Welcome to another ultralight design video of the UWS-4 Ultralight Airplane from the Ultralight Airplane Workshop. In this design series, we've been using a book from Dan Raymer, and it's titled Simplified Aircraft Design for Homebuilders. And in this particular video, we've reached the end of Chapter 3, where we figure out the size of the fuselage of our ultralight airplane. Let's get to it. I want to give a thanks to all the patrons of the Ultralight Airplane Workshop on Patreon. All of you guys are fantastic. One of the perks of being a patron is to get access to the Ultralight Airplane Workshop Discord server. I'm going to give a special shout out to Shane and Keith for being really active participants on our Discord server talking about airplane designs. We've been having a whole lot of fun. And I want to thank our newest designer tier patron, Nick. He's also been getting on our Discord server and having fun with us. If you might be interested in becoming a patron, I got a link here on this page that you can go to, and it's also down in the description of this video so you can just click on it. Go ahead and check out the various tiers, the various perks you get for those tiers, and see if you might like to join. Now let's move on to talk about the fuselage size for our ultralight airplane. As I said before, we've been using Dan Raymer's book, Simplified Aircraft Design for Homebuilders, to help guide us in the design of the UWS-4 Ultralight Airplane. Now I want to emphasize this series of videos is definitely not a substitute for getting Dan's book and reading it. I'm leaving out a whole lot of information that Dan covers in that book. Now part of that is because Dan's book is intended for slightly heavier home-built airplanes instead of ultralight airplanes. And in some cases Dan doesn't directly address ultralights, and so we have to kind of adapt it for ultralights. And he also talks about airplane configurations that we're not going to use, for example, canard configurations. So if you're really interested in what we're doing here in this design, and maybe you want to do something slightly different, I'd really encourage you to get Dan's book. I've got a link down in the description of this video that will take you to a page on the Ultralight Airplane website that is a link to several books that you can get that cover airplane design, ultralight airplane design, airfoil design, etc. And so you'll find a link to Dan's book there. And for full disclosure, if you use one of those links to get a book, the Ultralight Airplane Workshop will get a small cut of that sale. Before we hop into this, let's cover a little bit about what we learned in the last video. In that video, we figured out what we're going to do for the tail of the ultralight airplane. We decided on using an inverted V-tail, and a large reason for that was try to keep the tail out of the slipstream of the propeller. I want to try to reduce the drag on that tail, particularly because this airplane is intended to be a longer flight ultralight. I want to fly to nearby fields, but nearby is quite a ways away, so I'd like to have a little bit less drag on this ultralight so I can have a little more range. And then we figured out the service area, the span, the chord of the moving part of the tail, the control surface. We checked that aspect ratio to make sure it's quite a bit less than the wing so that we're more likely to have the wing stall before the tail does. We're not going to use any taper or sweep, it's a pretty straight tail. And the dihedral for this V is 40 degrees. And if you'd like to take a look at that video, I'll put a link for it up here in the upper right hand corner that you can click on, and that'll take you to the video. There's something I should point out here that I haven't done a good job in some of the previous videos. All this aerodynamic work that we're doing right now in this chapter in Dan's book, these are really crude estimates. Perhaps crude is overstating it, but these really are just first order estimates. And the reason we are doing these first order estimates is so that we can get some estimates of some other parts of the airplane that would be very difficult to do otherwise. And that would be, for example, the weights of the parts of the airplane. And from things like the last video, it'll help us calculate what the neutral point of the airplane is. That will let us calculate the longitudinal static stability of the airplane. And from all that, then we can come back and figure out if we need to resize any of these parts of the airplane that we're figuring out in this chapter. Now, the last thing we have to figure out in this chapter is the size of the fuselage. Now, Dan makes a really good point in this section. Typically, once you get to this point, there really isn't a whole lot left to decide on sizing your fuselage. You already know where your main wing is, you know where the tail is. That by itself will let you figure out what the aft length of your fuselage is. Really, the only thing left is the part in front of the wing. But if you really have absolutely no idea, Dan gives you an equation to try to get a rough estimate of what your fuselage length should be, but it's based on the gross takeoff weight of your airplane. So I decided, well, let's go ahead and plug this in, see what we come up with, and see how it compares to what the fuselage length that I come up on my own without using this length. So from video part 2.1 of our Aero design, we had a gross weight of 517 pounds. Once you plug it into this equation, we come up with a fuselage length of 15.5 feet. Now it's kind of long, but it's not an outrageous length. That's not bad. So the next thing Raymer talks about is fineness ratio. Fineness ratio is defined as the length of the fuselage divided by the diameter of the fuselage. And here in a moment we'll talk about how to calculate diameter because most of us don't have circular fuselages. So there's a certain range of ratios where you can get some fairly decent drag numbers on your fuselage, whereas if you go outside that range, you're really going to increase the drag. Now Horner, in his Fluid Dynamics drag book, says that 3, and it's really 2.7 but rounded up to 3, is probably the smallest ratio that you want for the finest drag. You go smaller than this and you start increasing the drag. Now you go larger than this and you may or may not increase the drag. And Raymer says for most home-built fuselages, we're getting significantly larger than 3 for our fineness ratio. We're getting up close to 6 or somewhere around in that area. But once you start going past 6, you start increasing the drag again. Now for 3 or smaller, you're generally increasing the drag just because you're getting turbulence behind the fuselage. When the fineness ratio gets to be above 6, you start getting into a different kind of issue. You have a significant amount of wetted area. And within that wetted area, you're generally going to have a lot of empty space. And particularly behind where you would have baggage in the airplane clear back to the tail. That's typically empty space that you can't do much with, but it has a lot of surface area. When you have a lot more wetted area, you're going to have a lot more friction drag. And let's actually go back and take a look at Horner's graph. So here's a graph from Horner's book on fluid dynamic drag. It's a figure 25. And so you can see here at different Reynolds numbers that the minimum here on the coefficient of drag is somewhere down around 2.7. But you can round it up to 3 reasonably. Well, now let's talk about how you can get a really rough, quick estimate of the diameter of your fuselage. What you can do is take the width of the fuselage, here represented by B, plus the height of your fuselage, and we're talking about the maximum width and maximum height. You add those two together, divide by 2, and you can use that as the diameter for your fuselage. Now this particular equation for estimated diameter of fuselage also came from Horner's book on fluid dynamic drag. That was on page 6-19 in a paragraph called Real Bodies. Well, what are we going to do on the UWS-4? So the Part 103 requirements for ultralights from the Federal Aviation Regulation in the US says we can only have one pilot. Well, that kind of helps us narrow down on how wide the fuselage is going to be. I'm going to start with 24 inches. That's not too bad for one pilot. Now sometimes you'll see this higher, especially if you want to be able to handle the heavier pilots. You can go up to 30, 36 inches if you had a really large pilot. Now I'm a pretty skinny guy, at least currently, so I'm going to start with 24 inches. Now down at my elbows, I might want to make it just a little bit wider, but I think at the shoulders 24 inches will probably be about right. Now for the height, I'm going to take whatever my seated height is. I'm going to put 4 inches underneath the seat. That's going to be for a crush area. In case I happen to have an incident where I impact the ground fairly flat, I'm going to have some crush area there to help reduce the G-force that I experience. I'm also going to have 6 inches above my head. Now that 6 inches will be for things like a helmet, for headphones, and if I'm in heavy turbulence, I'll be getting bounced up and down quite a bit, so it'll give me a little bit of room to bounce up and down without hitting my head against the ceiling of the fuselage. Now here's something I'm going to add that is not in Dan's book, but it's going to be some rule of thumbs that you can use to try to figure out the length of your fuselage, your first estimate anyway. Instead of using Dan's equation here, what I'm going to say is that the length of the fuselage aft of your wing, your main wing, and this is assuming a conventional configuration, not a canard, is generally going to be determined by the length of your tail. Now we've already talked about that back in the last video. We were figuring out where to place our tail. So length of the tail is a distance from the mean aerodynamic chord of the wing to the mean aerodynamic chord of the tail. So that will generally determine the length of your aft part of your fuselage in order to connect the wing to the tail. Now if you want to see more of the details about how to calculate that tail length, we did that in part 6. I'll put a link up here in the upper right hand corner where you can go back and see part 6 and see details on how we calculated that tail length. Now let's talk about forward of the wing. Now for ultralight airplanes, we typically have a tractor configuration or a pusher configuration. And for a tractor configuration, in general, your pilot's going to be seated at the CG. Kind of the navel up to the chin of the pilot, somewhere in that region, is going to be right at the CG of the airplane. And now I'm going to show you an exception to that rule of thumb. This is an ultracruiser. The ultracruiser uses a half VW engine, which is a pretty heavy engine. And in order to counter the weight of that engine out in the front of the airplane, the pilot had to be moved back aft at that CG location. And so wherever the feet of your pilot is then, you're going to have a firewall a couple inches in front of that, and then you're going to have your engine in front of that firewall. And so once you have that engine placed, you pretty much know what your fuselage length is going to be. So for a tractor configuration, it's pretty easy to figure out just how long that fuselage is going to be. Just placing that pilot in position and the engine in front of the feet of the pilot, that's a pretty good first estimate. Now for a pusher configuration, we're going to assume that the prop is just after the wing, just a few inches. That pretty much places that engine right at the aft part of the wing. In that kind of position, typically, now this is very rough estimate, the pilot's navel is going to be pretty close to the leading edge of the wing. Or the chin will be fairly close to the leading edge of the wing. So that's a good place to put your pilot to start with. And then in front of the feet of your pilot, you're going to need a little bit of crush depth, a little bit of room to move the pedals around. So you're going to need a foot for a very rounded nose, up to about 1.5 feet, something like that if you want a slightly more pointed nose. If you put that together, that'll pretty much determine your fuselage length. So this is a fairly good, rough first guess on where to put things for your airplane. Now you're going to refine all this a little bit later once you start getting more reasonable estimates for the weights of the parts of the airplane. Calculating where the CG is, then you'll start moving your pilot and your engine around to get all that to work right. Now if you want to do a design more like the Quicksilver MX, where you have a pusher configuration and the pilot does not have any sort of enclosure or windshield, putting that pilot in the same position relative to the leading edge is still a pretty good starting point. So here's what I have for the first estimate for the fuselage of the UWS-4 Ultralight Airplane. Now in the last video we figured out where to put the tail of the airplane, so all I really needed to do is connect up some booms from the wing to the tail. Now we already talked about why I decided not to do a single boom from the top of the cabin to the top of the tail. I'm going to have the front part of this boom be the same thickness as the thickness of the wing, and then it will taper off back here. Now you kind of ignore the part of the boom that's inside the wireframe of the tail. I don't exactly know what that structure is going to look like. One of the things I did do on this boom, as you probably remember in the last video, we talked about this boom slanting up a little bit. Let me take a side view real quick so you can see the boom slants up. I wanted to try to reduce the drag from this boom. I didn't want to use a round boom, so it's actually teardrop shaped. It's round on top and comes to a point underneath. But with the air flowing over it like this, it's a nice teardrop shaped, and so that should help reduce drag on this boom. I'm probably going to get some drag in this area here. The downwash of this wing is going to come down a little bit like this, so I could end up having a little bit of a drag area, an air bubble, an air separation in here. I might try to figure out a better way to fare this so I don't have some drag here. One of the things I did do to try to reduce interference drag is that I kept the width of the boom the same from up here at the thick part of the airplane to the trailing edge. That way I only have one direction of pressure recovery, that's along the wing. If I were making this boom slimmer in this area as it went back, that'd be a lateral pressure recovery area also, and that would end up causing interference drag. So right in here, the boom is straight laterally until I get past the trailing edge of the wing. So that will help reduce some interference drag. And I'm also going to have to do a little bit of work right in here to reduce interference drag. I'm going to have to put a fillet in here. Now let's move on to the cabin here. Now, something that will definitely change in the future is this area in here. This is where the engine's going to go. So there's going to have to be a cowling around here, which make this area much bigger. I'm not sure how I'm going to make good streamlining here, but at some point I'll get that figured out. But in here is where the engine will go, so this will be a little bulkier in the future. Now I want to have an enclosed cabin on this airplane if I can afford the weight, so I can reduce drag on this airplane so that we can extend the range. Let me make this cabin transparent and we'll pop in the pilot so we can see where he's sitting. So as you can see, I've placed the pilot with his navel and chin kind of dividing the area right here at the leading edge of the wing. So that's going to be my first estimate on where the pilot will be. My guess is that I'll end up having to move him a little bit farther forward. This engine is fairly far back here and going to be fairly heavy, and I think this pilot's going to have to come forward just a little bit more to get this CG close to the 25% core to the wing. And I've got about a foot of area from the feet of my pilot up to the nose. I've got a little bit more than 6 inches of crush depth under here, and I probably need to raise this area up here. I don't think I quite have 6 inches above his head. I'll probably just lower the pilot just a little bit. Now, one of the issues I'm going to have with this current setup is going to be interference drag right back here. Let me zoom in on this. Now here I've got a problem that I avoided back here. Here I've got this boom being the same width all the way back to the trailing edge. Well, I don't have that situation here. We have pressure recovery from the thickest part of the wing coming back to the trailing edge, but I also have pressure recovery here on the fuselage. So that's going to give me some drag problems right in this area. Now I can reduce those drag problems by putting a fillet in here. And I've also reduced the drag problems a little bit. If you remember from a recent video that I did on interference drag, I don't have this point coming all the way back to the trailing edge. Now if I had this coming all the way back to the trailing edge, I'd have even more interference drag. So since I've got this in front of the trailing edge, or it could have been way behind the trailing edge, but the prop would have had to been moved back too, at least I'm reducing it some. So I'm going to have to do a little bit of work in here to try to reduce the interference drag I'm going to have in this area. And also another reason I didn't bring this all the way back here is that I wanted to have better effectiveness on my flaps. If the fuselage had come all the way back to the trailing edge, my flaps would not have been quite as effective. So I should be getting better flow over these flaps, more airflow over the flaps by moving this contact point between the fuselage and the wing right here where this rear spar is going to be. Now back here where the pilot is in the cabin, one of the things I want to do here in the fairly near future is I want to do a mock-up. I want to do a mock-up of my seat and my pedal positions, try to figure out what a comfortable seating position is going to be for an extended period. And what I think I'm going to do is I'm just going to fix it up so that I can sit at my desk here in the office in the position I plan on being in the ultralight and seeing if I'm comfortable after sitting here at my desk in the sitting position for several hours. And then I will also do a little mock-up of a cabin to figure out what kind of roominess I want to have, how far in front of the pilot I want to have the instrument panel. I'm going to figure out where to put the control stick to make that comfortable. I'll work on how to do the rudder pedals, how to make those comfortable. Once I get all that figured out, then I'll come back here into OpenVSP. I don't think I mentioned that before. I'm using OpenVSP to do all this work. And then I'll put what I've learned into an updated fuselage shape. Now, if you remember, way back at the beginning, we used Raymer's equation to try to get a rough estimate of the length of our fuselage. Let's find out how my design came out compared to what that equation had. Now, that equation that we used, we came up with 15.5 feet roughly, given the gross weight that we're going to have. I used OpenVSP's measurement method to come up with the length. Now I'm measuring from the nose of the cabin back to 25% of the tail. Now the direct length is 18.5 feet, but that includes some height. We need to come down and look what the X length is. We come down here and we see it's 18 feet. So I'm actually 2.5 feet longer than what Raymer's calculation came up with. I kind of suspected that was going to happen because if you remember, back when we were looking at the tail geometry, let's take a look from the left side. I had to bring this tail up fairly high to get it out of the slipstream of the propeller. And I had to move it far enough back that I would be out of that 30-degree angle coming off the trailing edge of the wing so that the horizontal tail would not be in a disturbed area when we were in a stall. So that ended up moving this tail pretty far back. So it's really not too surprising. So at least we have a first estimate of what we're going to do for our fuselage. So what's the next thing we're going to do? Well, next thing is start working on chapter 4 of Raymer's book. And he's titled that Stuff in Some Stuff. So it's really going to deal with things that are not aerodynamic. Things that you need to put on your plane to make it usable, but really don't cover aerodynamics. And so it's going to be things about the pilot, which we've already talked a little bit about. Where to put your baggage, instruments, the front view looking out the cockpit. We'll talk about landing gear, where to place the engine, any engine cooling, how to deal with that. We talk about what we plan to do for the structure, the overall structural plan, and what to do about fuel tanks. So I'll cut this up into a few videos. It's too much for one video. Well, that's it for this video, guys. Thanks for watching.